with the original first review packet that I gave you guys. The first problem is asking about whether the extreme value theorem applies to each of these intervals. Of course, the extreme value theorem is really asking, are these functions guaranteed to have an absolute minimum and an absolute maximum? That's what that theorem's about. So really what I'm asking you is, can you be sure that these functions have absolute mins and maxes on this interval? So this function here, remember the extreme value theorem says if a function is continuous on a closed interval, then it will have an absolute min and an absolute max. So really what you're doing is you're asking, first of all, is this function restricted to a closed interval? In other words, an interval containing the boundary points. Second of all, even if it's restricted to a closed interval, is the function continuous on that interval? In other words, is it defined on that interval? This function here in part A is restricted to a closed interval. These brackets indicate that it's a closed interval. That's like the interval -1 less than or equal to x less than or equal to +1. So that's good. Is this function continuous on this interval? Are there any bad values that exist on this interval? The answer is yes, this function is continuous on this interval, because the only bad value that you could plug into this function would be x equals 2, but that's not contained inside this interval. So the extreme value theorem does apply to this function on this interval, and that means that it does have an absolute minimum and an absolute maximum on this interval. Part B, the analysis is exactly the same. The interval is, again, closed. That's good. The problem, though, is that this function is not continuous on this interval because it's not defined at x equals 2, which is inside this interval. So the extreme value theorem does not apply to this function on this interval, which means that you are not guaranteed to have an absolute minimum or an absolute maximum. Maybe you get one anyway, but you can't be sure. This function here, it's continuous everywhere, and that's great. The problem is that this interval is not a closed interval. It's sort of half closed, right? Like it includes the boundary point 0, but not 3. Written in interval in the sort of inequality notation, this is the interval 0 less than or equal to x, strictly less than 3. So because it doesn't include the 3, the theorem doesn't apply, and you don't know whether it will have an extreme value or not. Number 1, suppose the sum of two numbers is 10. Find the maximum value of their product. This is an optimization problem. Let's call our two numbers x and y. Then what we want to do is maximize the product of x and y. In other words, we want to maximize the function p, which is just x times y. We want to find the maximum value of this expression. But as with every optimization problem, the function we're trying to maximize involves two variables, so we need to use the constraint to eliminate one of those variables. The constraint is that the sum of the numbers must be 10. In other words, x plus y must be 10. We can solve this constraint for one of the variables, say y equals 10 minus x, and then substitute back into the function we're trying to maximize. That will give me p is equal to x times 10 minus x, which is just 10x minus x squared. Now that we've written our objective function as a function of just one variable, we can use the usual tools that we have to find mins and maxes. Namely, we can take the derivative, set it equal to 0. So I get 10 minus 2x, set that equal to 0. If you solve that equation, you'll get x equals 5. So x equals 5 is apparently the value that will do the job. Now, all we really know is that this is a critical point, right? How do you really know that this is the x value which produces the biggest product? Maybe it's a minimum. Maybe this x value produces the smallest product. Well, the thing is, the only answer to the question could be 5, right? I mean, 5 is the only value that really we could be expected to find here, because there are no boundary points in this problem. And there's just this one critical point, so like this has to be the one that we're looking for. So we don't really have to think about, oh, is it a min or a max? Well, that's got to be the thing we're looking for because it's the only one we got. So if x is equal to 5, going back to this equation, going back to the constraint equation, you can see that y also has to be 5. So x equals 5 and y equals 5. That means that the product would be 25. So the largest product that you can make is 25, which occurs when both x and y are 5. Number 2, identify both coordinates of any relative max and min. That's a very old kind of problem. Just take the derivative, set it equal to 0. So 18x minus 6x squared, set that equal to 0. That will factor as 6x quantity 3 minus x equals 0, I think, right? 18x minus 6x squared, yeah. So that gives me two solutions, x equals 0, x equals 3. I'll plot these on a number line just to sort of understand what these points are. So I'm doing a sign analysis for f prime. Here at -1, if I plug those values, if I plug -1 into the derivative here, that term would be negative, this term would be positive, so I think the whole thing is negative there. And then if you pick a value inside this interval, you should find it's positive, and if you pick a value inside this interval, you should find that it's negative. So the original function must be decreasing, then increasing, then decreasing. That tells me that this is a min, and this is a local maximum, or a relative maximum. So that's part A. Oh, I guess they want you to find both coordinates, right? So we should find the y values corresponding to these x values as well. So to do that, I plug into the original function. F of 0 is obviously 0. So we have a min at 0, 0. And f of 3 is 9 times 3 squared. So that's 9 times 9, which is 81. Minus 2 times 3 cubed. 3 cubed is 27. So that's 81 minus 54, which is 27. So I have a max at 327, assuming I didn't make any mistakes. And then finally, part B, find its absolute minimum and absolute maximum values on the interval 1 to 4. These guys are relative minimums and relative maximums. They may or may not be the absolute minimum and the absolute maximum. Before we even do this, how do we know for sure that this function has an absolute minimum and an absolute maximum on this interval? Like, maybe we're wasting our time. Well, the answer is that we are restricting the function to a closed interval, and this function is continuous on this closed interval, so the extreme value theorem guarantees that it will have an absolute minimum and an absolute maximum on that interval. So how do we figure out the absolute minimum and maximum? In general, what you do is you make a list of your critical points and your boundary points, and you just plug them all in to the original function and see which one gives you the biggest and smallest values. We've already evaluated the original function at these critical points, right? So all we have to do now is consider the boundary points, which are 1 and 4. Oh, and by the way, you should always ask yourself, are these critical points actually inside of the interval that we're given, right? Like x equals 0 is a critical point, but is that inside the interval? The answer is no, it's not, which means that for the purposes of this problem, we shouldn't even think about 0. So forget about 0, but 3 is still admissible, right? So that's still possibly one of the absolute mins or maxes. But we need to look at the value of the function at the boundary points, 1 and 4. So f of 1 would be, what is this function again? So that'd be 9 minus 2, which is 7. And finally, f of 4, that would be 9 times 4 squared, so 9 times 16, minus 2 times 4 cubed, which is 64. So I don't know what that is. 9 times 16 minus 2 times 64, I get 16. So out of all of these guys, what's the largest y value? this one. So not only is 3, 27 a relative maximum, it happens to be the absolute maximum on this interval. And of these three values, the smallest one is the 7, which tells me that our absolute min is at 1, 7. Assuming I didn't do any stupid arithmetic mistakes when I was calculating those numbers. Number 3, Pepsi wants to make a closed cylindrical can. Okay. They can have 150 pi square centimeters worth of metal for the surface. Find the dimensions that yield a can of maximum volume. So as always in an optimization problem, you want to ask yourself, what are you trying to maximize? In this case, that's the volume. So my objective function is just the volume formula for a can, for a cylinder, which is pi r squared h. So you want to find the maximum value of this function. Oh no, but this function depends upon two variables, r and h, so we have to eliminate one of them. That means we have to use the constraint. What's the constraint? It's that the surface area must be 150 pi. The surface area, of course, is 2 pi r squared plus 2 pi r h. You don't have to have that memorized, although it is pretty easy to work out if you know where it comes from. So that expression there has to be equal to 150 pi. That's our constraint. So I'm going to solve this equation for one of the variables and then substitute into my objective function. I think it makes sense to solve for h. It's going to be a lot easier to solve for h than for r, right? If I had to solve for r, then I'd have to like take square roots and stuff. So to solve for h, I'm going to start by just isolating the term containing the h. So that's 150 pi minus 2 pi r squared equals 2 pi r h. Before I do anything else, you might notice everything's divisible by 2 pi. So let's just divide everything by 2 pi. That gives me 75 minus r squared equals rh. So dividing everything by r, I will have h by itself. So that's 75 minus r squared over r equals h. Now I take this and I substitute into my volume equation. So volume is pi r squared times h, which is the 75 minus r squared over r figure. So now this is a function of one variable. I can do the usual techniques to find its maximum value, its critical points, blah, blah, blah. Before I take the derivative, I should simplify. This r squared, one of the r's here will be canceled by that r there, leaving me with just pi r times quantity 75 minus r squared. And then you should distribute. So that's 75 pi r minus pi r cubed. So now if I take the derivative, I get v prime is equal to 75 pi minus 3 pi r squared. Set this equal to 0 and solve. I'll point out right away, every term is divisible by 3 pi, so maybe I'll just divide everything by 3 pi. You don't have to do that, but well, you're going to do that anyway, right? I mean, I think you'd start by, yeah, let's just do it this way. Add 3 pi r squared to both sides, divide by 3 pi. You get 25 is equal to r squared, so r is equal to plus or minus 5, but we're talking about a radius. That has to be a positive number, so r has to be 5. How do I know that? Now that's just a critical point. Maybe it's a local minimum, right? Maybe this is a value of r which minimizes the volume. How do I know that it's going to maximize the volume? Well, I know because this is the only value that could possibly be the answer to the question, right? Like there are no boundary points, there are no other critical points. This has got to be it, so the end. So this is the r value that maximizes the volume. What is the volume corresponding to that r value? Well, to find out, maybe you think you need to go back to this original equation and then you say to yourself, oh, I need to find h, which means I need to go to this guy and plug in 5 for r there and then go back to this guy. No, if you just go back to this version of the volume formula, in that version of the volume formula, there is no h, there's just an r, so I'm just going to use that one. 75 pi minus 3 pi, or sorry, I'm looking at this formula. 75 pi r, which is 5, minus pi times 5 cubed, which is going to give me So basically 5 times 75 minus 5, is that 250 pi? Is that right? That's a lot of work, and I kind of want to make sure I didn't make a mistake. I tend to make a lot of mistakes when I'm typing on the computer, especially when I'm like explaining what I'm doing as I'm doing it. Blah, 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 blah. Okay, it doesn't say what the maximum volume is, but it does say that it occurs when r is equal to 5, which is what we found, and h is equal to 10. I didn't bother finding h. But anyway, if I made a mistake, then it's a small one, just some arithmetic mistake somewhere. Number 4, identify both coordinates of all relative maxes and mins. Okay, that just means I need to be looking at critical points. So I'm going to take the derivative, set it equal to 0. I need to use the product rule. So this is 1 e to the 4 minus 2x plus x times e to the 4 minus 2x times negative 2 because of the chain rule. So that's f prime of x equals, I think you can factor out an e to the 4 minus 2x from both terms, so I think I'll do that. That leaves me with 1, and then in this term I'm going to be left with a negative 2x. If I set this equal to 0, obviously this factor here gives me the solution x equals 1/2. This factor here doesn't produce any solutions because exponentials are never 0. So this is the only critical point. Is it a local minimum or a maximum? For that, I'll do a sign analysis. So here's a sign analysis for f prime. If I imagine plugging in a number from this interval, like, I don't know, 100 or something, is it positive or negative? Well, this factor here, remember I'm plugging into f prime, this factor is always going to be positive. Exponentials are always positive. So if I plug in 100, that factor is going to be positive. But this factor will be negative, so I think this guy is going to be negative. A similar argument will tell you that this guy, that interval is going to be positive. So the original function is increasing, then decreasing. So this has to be a local max. They want us to find both coordinates, so we should find the y coordinate of this 1/2 value. F of 1/2 is 1/2 times e to the 4 minus 2 times 1/2, which is 1/2 e to the 3rd, I think. So the coordinates are 1/2 comma 1/2, 1/2 e cubed. And that is our local max. That's all the critical points. Now we should find the absolute min and max values on this interval. I know that the absolute min and absolute max values do exist because this function is continuous on this interval, and this is a closed interval, so the extreme value theorem applies. All I need to do is make a list of critical points and boundary points. I've already done the critical points. It's this guy right here. So I just need to look at the value of the original function at the boundary points. F of 0 is definitely 0. So that gives us the point 0, 0. And then f of 2 is 2e to the 4 minus 4. So that's 2e to the 0, which is just 2, right? So I think that point is just 2 comma 2. Okay, of these three y values, which one is the smallest? Definitely 0, because whatever this number is, it's a positive number. So this has to be the absolute min. As far as the absolute maximum, which of these two values is bigger? 1/2 e cubed or 2? Yeah, 1/2 e cubed is. I mean, if you think about it, e is a little bit bigger than 2. It's like 2 point something. So if you take that and cube it and then cut it in half, you're looking at something around 8. So yeah, this guy is not just the local maximum, but also the absolute maximum. Okay, number 5, a rectangular field, blah, 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 blah. The area is 225, bounded on 3 sides. Okay, it looks like there's not any fencing along the river. It's just these 3 sides. Okay, find the dimensions of the region that have the minimal cost and maximal cost. Notice they're asking for two things here, and that makes sense to me because obviously we're going to get critical points like usual, but also we're going to be confined to a closed interval here because of this guy. Like the length and the width must both be at least 1 foot. I don't know which of these you want to call the width and which one you want to call the length, but what this is saying is that x and y are both at least 1. So x has to be at least 1 and y has to be at least 1. As you'll see in a minute, this fact here really means that x has to be less than or equal to 225. So let's just try to understand what's going on. So I'll come back to that, the meaning of that inequality there in a second. So first of all, the area has to be 225. That's a constraint. Okay, so what is the area? Well, it's x times y. So x times y equals 225. That's my constraint. I know I'm going to have to solve that constraint for one of the variables. I might as well just do it now. So y is equal to 225 over x. This is where this figure comes in. If y is at least 1, then that means that x can't be any bigger than 225. Like if x is bigger than 225, then this fraction would be smaller than 1, which would contradict this. So really, this is just a sneaky way of saying that x has to be less than or equal to 225. So really what we're told is that x has to be between 1 and 225. In other words, x is in the closed interval 1 to 225. So the fact that we've got our x value confined to a closed interval means the extreme value theorem's kicking in. We're going to be guaranteed to have an absolute min and max. Which one is which? We'll just plug them all in and compare, right? But anyway, we need to write down the objective function, right? The thing we're trying to minimize or maximize, which is we want to find the minimal and maximal cost. So we need to write down a formula for the cost. So what is the cost? Well, there's two kinds of materials that we're going to be paying for. The first one is wire. The fence parallel to the river, so that's this portion, is made of wire, and it costs $1 per foot. So how much wire are we using? Like what length of wire? That would be y units of wire. And how much does it cost per unit of wire? Well, $1. So it's y times $1. That's the cost of the wire that we're using. The wood fencing is these two sides here. How much wood fencing are we using? Well, 2x, because there's two of these. But the cost of the wood fencing is going to be the amount of wood fencing that we're using times the cost per foot, which is another 2. So that means the cost function is y plus 4x. I've already solved my constraint for y, so I can just right away replace this y with 225 over x. So I get this. Now I'm going to take the derivative. C prime is negative 225 x to the negative 2 plus 4. I'm going to set this equal to 0 and solve. So this is negative 225 over x squared plus 4 equals 0. In other words, equals negative 4, right? So, divide both sides by negative 1. You can kill off the minus signs. You get this. And then multiply both sides by x squared. I get this. Divide by 4. I get this. Take the square root. I'm not going to worry about the plus or minus because I only care about positive values. These are perfect squares. Square root of 225 is 15, I think. Right? 15 squared. Yeah. 15 over 2. So that's the x value that I get. So they want to know what is the dimensions. Well, let me just find the x value. I can easily find the y value by going back to this guy and plugging in. I'll just find the x values. So I've got 3 x values to consider, right? I've got this critical point that I just found, and I've got these 2 boundary points, 1 and 225. What I need to do is plug each of them into my cost function, see which one produces the biggest, which one produces the smallest. Use this version of the cost function because that way you don't have to find the corresponding y value for each one, right? This version of the cost function only depends upon x. So C evaluated At 1, that first boundary point, you know, I'm looking at this formula right here, that would be 225 plus 4 is a 229. C of 15 halves would be 225 over 15 halves plus 4 times 15 halves. So what is that? That's like 225 times the reciprocal of 15 halves plus, I think that's just 30, right? Because that's like 2 times 15 equals, so what is that first term? Dividing by 15. Oh, this whole thing's just 60, isn't it? I'm pretty sure that's just 60. And then finally, C of 225 is, you know, if I make an arithmetic mistake in doing these problems, it's not a big deal. I think you'll understand what I'm saying regardless. C of 225 is, where's my C? It's this guy right here. If I plug in 225 into that, I get 225 over itself plus 4 times 225. That's 1 plus whatever this is. Is that 900, I think? Yeah, so 901. So of the costs, it looks like the maximum cost is $901, and that occurs when you choose X to be 225, and the minimum cost is $60, which occurs when you choose X to be 15 halves. Is that right? These longer problems, I kind of want to make sure I didn't do anything stupid. Max cost when X is 225, yep, I agree with that. Min cost when X is 7.5, yeah, that's my 15 over 2. Cool. What's next? Are we done with optimization? Yes, we are. Good. Okay, this is rate in, rate out. So, hope you'll excuse me. I'm going to use Desmos rather than the stupid graphing calculators because, I mean, you know, how would I show it on the screen? It's not very nice. Okay, so the rate at which rainwater flows into a drain pipe is modeled by the function r, where r is blah, blah, blah. Okay, that's my rate in function. Let me just go ahead and punch that into Desmos right now. So r of t is 20 sine of t squared over over 35. And that's occurring for t between 0 and 8. So I'm just going to restrict and you should do this in your calculator as well. I'm going to restrict my x values to that interval. Like, you know, why would you look at anything else, really? Blah, blah, blah. The pipe is partially blocked, allowing water to drain out at a rate modeled by blah, blah, blah. So d of t is, and of course this is a calculator problem, like all the rate in and rate out questions are. 0.4 t squared plus 0.96 t, and that is my rate out. Okay, so this is rate in, and this is rate out. I think I'm going to change the colors on these graphs. I feel like rate in should be green because it's positive, and maybe rate out I'll make red because it's negative, just to make it easier for me to remember. I do this as well. Okay. I can see the graphs kind of go off the screen, so I'm going to change my y values so that I can see them all. Maybe 30. Yeah, that does the job. So my window right now is 0 to 8 and like -1 to 30. And that gives me this picture. That's a pretty good picture. Okay, so now that I've got these graphs, let's answer some questions. How many cubic feet of rainwater flow into the pipe during the 8-hour time interval? That is not asking you how much water is there at the end of the interval. They're just asking how much water flows in. That's going to be the integral of the rate in function. So 0 to 8 of r of t dt gives me 76.5. Okay. Part B. Is the amount of water in the pipe increasing or decreasing at time t equals 3? Give a reason for your answer. Well, graphically, it looks like at t equals 3, the red graph is above the green graph, which means the rate out is greater than the rate in, which means that the overall amount of water is decreasing. Alternatively, you can do, as always, the rate in minus the rate out, at that moment in time. And you can see that this number is negative, which is telling you that overall it's decreasing. Part C, at what time between 0 and 8 is the amount of water in the pipe at a minimum? That's either going to be, either this intersection point or one of the boundary points between 0 and 8. So, wait, what do we want? We want the minimum value? Okay, well, I can kind of probably just think about it. If I look during this initial period, the rate out is higher than the rate in. So during this initial period, the overall amount of water is decreasing. After this intersection point, the functions trade places, and then the rate in is greater than the rate out, which means during this time period, the overall amount of water is increasing. So if the overall amount of water is decreasing, 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 and then at this moment it switches to increasing, 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 surely this right here is the moment at which the minimum occurs. So what is that minimum? Well, I can see, and you can see using the intersection function on the intersect function on your calculator, the moment at which this occurs is 3.272. But this 6.022 value is not the amount of water in the tank, right? Like that's the value of these functions. Those are rate functions. So to find the amount of water, they don't even ask you what that amount is, right? They just want to know, like, at what time does it occur? So 3.272. If I wanted to figure out how much water there was at that moment, then I'd take the initial amount of water, which I don't even know if there is an initial amount. Yeah, 30, and then I'd add the integral of the rate in and subtract the integral of the rate out up to, the integral from 0 to 3.272. Part D, the pipe can hold 50 cubic feet of water before overflowing. For T greater than 8, water continues to flow into and out of the pipe at the given rates. In other words, I think they're just saying that these two functions continue to apply even beyond time t equals 8. Right, but do not solve an equation involving one or more integrals that gives the time w when the pipe will begin to overflow. Okay, so really, this is sort of interesting. What they're saying is, so w is the time at which the pipe overflows. Okay, so w is a t value. It's a time at which the pipe overflows. And what does it mean for the pipe to overflow? It means that the amount of water in the pipe will equal this 50 cubic feet here, right? Because that's the maximum amount that it can hold. So the moment at which the current amount of water reaches 50, that is the moment at which the pipe overflows. So here's what I'm going to do. I'm going to write an expression for the amount of water at time t, and then I'm going to simply set that equal to 50. And the solution to that equation will be the w that they're looking for, right? So we don't have to solve the equation because they say write but don't solve. So all I have to do is write down a formula for the amount of water at time t, set that bad boy equal to 50, and then that's my equation. So what is an expression for the amount of water at time t equals, let me be clear. It almost looks like I'm saying that t is equal to 50. I'm not, right? I'm saying that the amount of water at time t is 50. T is not 50. The amount of water at time t is equal to 50. Okay, so what's a formula for the amount of water at time t? It's the amount of water that you started with, which I think was 30. Yeah, 30. Plus however much water you added from 0 to t. So that's the integral from 0 to t of the rate in function. You can just write r of t. That's the rate in, right? Yeah. Minus the integral from 0 to t of the rate out function, which is d of t. Oh, I'm making a mistake though, right? I shouldn't be using the same variable here as I am in this upper limit of integration. So that's fine. I just need to change these to something else. That's just a notational thing, right? You're not supposed to use the same variable. So this guy here is an expression for the amount of water at time t. And if I set this equal to 50, I'm saying, okay, we want the amount of water at time t to be equal to 50. So W, this magical time at which the pipe overflows, W is the solution to the above equation. It's the value of t, which would make this true. Okay, and that's all we have to say for that. Okay, now we're moving on to this one. Is this the last one? Yeah, this is the last one. And I think I'll stop here. I don't feel like recording a 3-hour video. There's more review problems in other PDFs, but I'll do those later or tomorrow or something. The amount of water in a storage tank in gallons is modeled by a continuous function on the time interval, blah, 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 routine, okay, the rate at which water enters the tank. Okay, so it's a very similar kind of problem. We've got a rate in, we've got a rate out. One thing that I notice is that the rate out function is this piecewise function. I don't think that, as far as I'm aware, there's not really a way of graphing piecewise functions on your calculator. So you're not really going to be able to graph g of t. Of course, you have a picture of these functions. You won't really need to, though. Like, you don't need to input that g function into your calculator. You will need to enter the f of t, though, right? So this is 100t squared sine of square root of t. Yeah. And this is for what values? For x between 0 and 7. I can already see this graph is going way off my screen, so let me make my y value a lot bigger. Wow, you have to make it pretty big, don't you? Like 5,000 maybe is a good value? Yeah, that's pretty good. Let's leave it at that. Oh, I guess I could have just looked at the graph to see what a reasonable window would be, right? 2,500. Let's just make it 2,500 to match what they have. That was stupid of me. Anyway, okay, anyway, so this is the rate in, and the rate out is like this piecewise constant function. The graphs of f and g, which intersect at t equals 6.17, so this moment right here, that's t equals 1.617, and t equals 5.076, so that's this guy right here, are shown in the figure above. At time t equals 0, the amount of water in the tank is 5,000 gallons. Okay, part A. How many gallons of water enter the tank during the time interval 0 to 7? Well, they just want to know how much water enters the tank. They're not asking how much water there is in the tank at the end of the interval. They're just asking how much water flows in. And that would be just the integral from 0 to 7 of this rate in function, which is that number right there, 8,000 something. Okay, so that's part A. Part B, on the interval, find the time intervals during which the amount of water in the tank is decreasing. Give a reason for each answer. So the amount, what we could say for part B is the amount of water is decreasing when the rate in is less than the rate out, right? When the rate out is bigger. So, in other words, when f of t, this sinusoidal curvy function, is less than g of t, this piecewise constant function. So anytime the curvy guy is below the piecewise constant guy, the amount of water is going to be decreasing. So, for example, this first interval here, that's true, right? So that's from 0 up to this intersection point. The thing is, they give you this intersection point. You don't even have to find it. So it's from 0 to So certainly from 0 to 1.617. During this next time period, the rate in is bigger, so not then. But then at 3, the rate out constant guy is bigger again, up until this intersection point, right? So also from 3 to that other intersection point here, which is the 5.076 guy. And let's see, and then during this last time period, the rate in is greater, so the water is increasing. So it's just those two intervals. Finally, part C, at what time t is the amount of water in the tank the greatest? To the nearest gallon, compute the amount of water at this time. Justify your answer. Well, there's a couple ways that you could do this. Maybe I'll talk for longer than I need to. Let me tell you the fast way, and then I'll just sort of explain. So what do I want? The greatest amount of water? Yeah, the greatest amount of water. So here's what I'm going to do. I'm going to sort of color in my graph a little bit. The coloring tools on this program are just absolute trash, but I'm going to do the best that I can. Anyway, so during this first time period, and what do we want? The smallest amount? No, the greatest amount. Okay, greatest amount. During this first time period, you're losing water, right? How much water do you lose during this time period? Overall, how much water do you lose? I claim, some water's going out, but some water's going in. The overall amount that you lose is actually the area between these two curves. Okay, it's the area between those two curves. Why is that? Well, basically, how much water flows out, it's the area underneath the straight line, right? Which includes, it's like this whole rectangle here, okay? But during that time, you also gain some water, which is the area under the sine curve, okay? So the difference between those things is how much you lose overall. So over this time period, the overall amount of water in the tank decreased by this red area right here, okay? Then during this time period, the water is increasing. So I'm going to use a green. Okay, that's still red for some reason because this is considered an outline apparently. You gain a bunch of water during this period. How much? It's the area between these two curves, okay, for the same kind of reason, right? You're gaining water, you're losing water, but overall, the amount by which the water increases, this is green area here. And then at this point, you're losing water again, so I'll switch back to red. I almost swore on the video. I came very close. So this guy right here is a loss, right? So you're going to lose all that water. And then finally, up here, we gain some more water again. So like that. So just looking at this picture, like when do I have the greatest amount of water? Well, I start with some amount of water, and then I lose this red amount, and then I gain this green amount, and then I lose this huge red amount, and then I gain this moderate green amount. So I think the water maxes out right here at 3. Okay, because yeah, you lose some water here, but I think you gain more than you lost by going through this green region, right? And then you're best off just stopping right there, because if you go any further, like you lose a ton of water and you only gain some of it back. So I think right here at x equals 3 is what you're looking for there. I said I was going to stop and stop there, but I think maybe I'll just keep going and talk about the next review packet. I'm definitely not going to do all of it. Okay, so this is the second PDF. Tragically, the Kool-Aid man has sprung a leak. When he first springs a leak at t equals 0, he is filled with 200 gallons of Kool-Aid. I don't even know if you guys know what the Kool-Aid man is. Whatever. He is currently losing Kool-Aid at a rate modeled by blah, blah, blah. So that's the rate out. They immediately begin to fill him back up with Kool-Aid at a rate modeled by blah, blah, blah. So that's the rate in. How much Kool-Aid is lost during the first 2 minutes? Not net loss, just how much flows out. Yeah, that's a good piece of clarity. Let me just put these two functions into my Desmos thing here. So I've got f of t, which is 8 natural log of t plus 3. That's my rate in. No, that's my rate out, right? Let me color this red. Otherwise, I'll get confused. So that's rate out. The rate in is the g. So that's plus 10, 5 cosine 2t. Yeah, and that's green. So rate in. Cool. So how much flows out? That would be the integral of the rate out function. So that would be the integral from 0 to 2 f of t dt. So I think that amount. Part B. At time t equals 3 is the amount of Kool-Aid increasing or decreasing. You could look at the graphs and like see which one is bigger. I don't even see the graphs on here. I'm going to reset to the standard viewing window, like -10 to +10, just to reorient myself. Okay, I can kind of see the graphs. When is all this happening for? Like, what is the interval under consideration? I don't think it says. So I don't know. Whatever. But at time t equals 3 is the amount of Kool-Aid increasing or decreasing. You can look at x equals 3, which is like right here, and just be like, oh, looks like at t equals 3, the rate in is greater. So therefore, the overall amount of Kool-Aid is increasing. Or you could evaluate the functions. Like you could do rate in minus rate out. You could do g of 3 minus f of 3. That's a positive number, so overall, the overall derivative is positive, so it's increasing. Part C, write an expression a of x involving a single integral that gives the amount of Kool-Aid at time x. Well, so that's going to be your initial amount of Kool-Aid, which is 200, plus the amount of Kool-Aid that you gain up to time x, which is the integral from time 0 to time x of the rate in function, which is, I think that's g, right? Yeah, that's g of t dt, and I'm okay because this x is different from the variable here, minus the amount that you lost from time 0 to x, so integral from 0 to x f of t dt. And that'll be a formula for the, involving a single integral, it says. Oh, well, okay, a single integral. Well, it's not a big deal. You just need to, combine those two integrals into a single integral, because you can rewrite this as plus integral from 0 up to x quantity g of t minus f of t dt. There, that's a single integral. Voila. Part D, find and interpret using correct units a prime of 5. Well, like, the derivative of the overall amount of stuff is always just the rate in minus the rate out. So, like, you could just write that immediately, or you could take the derivative of this formula. But you'd have to remember how to take the derivative of integral functions. It's the second fundamental theorem of calculus. Derivative of 200 is 0. The derivative of this integral function, do you remember how to take the derivative? You just take this guy and you put it here, right? So you get g of x minus f of x. Or you can just always remember that, like, the overall rate of change of the amount of stuff, in other words, the derivative of the amount of stuff, is always just the rate in minus the rate out. So anyway, find and interpret. So what is a prime of 5? You know, I mean, it's just going to be g of 5 minus f of 5, which is negative 10 point something, right? So negative 10.8 or whatever. What are the units? Well, the units of f and g are gallons per minute. So So this is in gallons per minute. So what this is saying is that at time 5, overall, the Kool-Aid Man is losing 10.8 gallons per minute overall. That's what that's saying. This problem goes on and on. The rescue effort is concluded at time t equals 10 when the leak... Oh, I thought it was going to say the rescue effort is concluded when the Kool-Aid Man just died or they gave up or something, but it seems like they fixed him up. The rescue effort is concluded at time t equals 10 when the leak is patched. Find the maximum and minimum amount of Kool-Aid in Kool-Aid Man between time t equals 0 and 10. So I'm just going to restrict my x values to 0 to 10, since that's the interval that I'm actually interested in here. And then I'll just adjust my y values so I can clearly see everything on the screen. That's pretty good. Okay, so that's what my graphs look like. They want to find the minimum and maximum amount of Kool-Aid. Well, you know, as I sort of said in the previous problem, and if you want more details, watch what I said about the last question of the first review. It's like, I don't know, 5 minutes before. It's the problem I was doing right before this one, so like 10 minutes earlier in the video or something. If you want more details on why I'm doing what I'm doing here, but what you can do is you can look at the area between the curves. So green is the rate in. During this time period, I'm overall gaining water or gaining Kool-Aid. And how much Kool-Aid do I gain overall? I mean, you gain some Kool-Aid, but you also leak some Kool-Aid. The net overall amount that you gain is the area between these two curves. Okay, so you gain this stuff right here. So imagine this area filled in with green. And then you lose a ton of Kool-Aid. The area between these two curves, right? And then you gain a little bit back, right? Then you gain a little bit back. It looks like a tiny bit. And then, my God, you just keep losing Kool-Aid. Like, the rate out is, I mean, is that really right? That makes me worry about Kool-Aid Man. Is f of t really the rate out? Did I misread this problem? I hope not, because then all my answers would be wrong. He's currently losing Kool-Aid at a rate modeled by, yeah, that's the natural log function. So, yeah, so he's just losing tons and tons and tons of Kool-Aid. So from that alone, you can pretty much figure out when he maxes out. I think it's right here at this intersection point, because he initially gains a good amount of Kool-Aid, right? It's the area between these two curves. Then he loses a ton, or quite a lot anyway, right? Like certainly more than he gained initially here. And then he gains a trivial amount back, certainly not enough to compensate for all the losses here. And then after that, it's just all losses. Like he's bleeding out. So I think right here is the maximum, okay? Definitely. That moment right there is the time, that 0.732 figure is the time at which he has the maximum amount. Now, what is that maximum amount? It's not the 10.535, right? These are rate functions. This is the rate at that moment. The amount that he has at that moment is, well, he started with some, right? He started with 200 gallons. And then, up until this moment, from 0 to 0.732, how much did he gain? That would be the integral from 0 to 0.732 of the rate in function, dt, minus the integral from 0 to 0.732 of the rate out function. So I think that is the amount that he has. That's how much he has. That's the maximum amount. As far as the minimum amount over the time interval from 0 to 10, I think that's pretty clear from what we were saying earlier. Like, because he's just losing so much Kool-Aid during this time. He's going to be at a minimum, I think pretty obviously, at the very end of the interval, like at x equals 10 or time equals 10. So, how much does he have at that moment? I'll just change these limits of integration to 10, and you'll have your answer. Okay, 141. So he lost more than a quarter of his Kool-Aid, which sounds pretty bad, but I don't know Kool-Aid biology. Oh my god, there's more. Okay. Part F, after time t equals 10, Kool-Aid is continued to be there's obviously some copying and pasting stuff that happened here. Okay, after time t equals 10, he keeps receiving Kool-Aid, I think is what it's saying, but at a different rate, at a totally different rate. Okay, at a totally different rate. Now he's getting more Kool-Aid. At what time will he return to his starting level of 200 gallons? So I think, I think the understanding of the problem is that after t equals 10, the leak has been patched, right? Like he's not losing anymore. So he's just gaining this. So forget about the old rate out function. Forget about the old rate in function. There's just this one function. Okay, there's just this one function. And we want to know when will he return to his starting level of 200 gallons. Well, at t equals 10, how much Kool-Aid did he have? We just found that. It's this 141 value, right? So what I want is I want it to be true that 141.8943 plus the integral from 10 up to some mystery time, that I don't, stupid thing, 10, there we go, of this h of t dt thing, right? Like this will give the amount of Kool-Aid that he has at time x, where x is a time later than 10, because this is how much he has at time 10, and then this is how much is added from time 10 to this later time x. And we want this to be equal to his original amount of 200. And you have to solve this equation. How are you supposed to solve this equation? Well, first of all, you can subtract the 141 from both sides, right? And that'll give you just the integral of h of t dt. Oh, why am I having trouble? There we go. Equals 200 minus 141.8943, which is 58.1057. And I need to solve this. How do you do it? Well, you know what h is. It's 1 over root t minus 9. So I have integral from 10 to x, 1 over square root of, what is it, t minus 9? T minus 9 dt equals 58.1057. So the thing is, I'm just going to evaluate this integral. It's going to be some expression involving x, and then I can solve the resulting equation for x. So what is this integral? Well, you got to find an antiderivative for this guy, right? So that's like t minus 9 to the negative 1/2. I think an antiderivative would be t minus 9 to the positive 1/2 times 2. Right? If I take the derivative of this guy, the 1/2 comes down, kills the 2, I subtract 1. Yep. So that is the antiderivative. And, I don't have a good symbol for the big vertical bar in this program, so I'm just going to write from 10 to x in words, and that's supposed to be equal to 58.1057. So plugging in 10, I get 2 times 10 minus 9 to the 1/2 minus plugging in x, 2 times x minus 9 to the 1/2 needs to be equal to 58.1057. This first term is just 1 to the 1/2, which is 1 times 2, so the whole thing's just 2. So 2 minus 2, and this, 1/2 is just a square root. So we have this equation here. 58.1057. So I just need to solve this equation. So subtract 2, negative 2 root x minus 9 equals 56.1057. And then divide by negative 2, I get that equals 56.1057 divided by 2 and 28. So it's like negative, I should have kept some more decimals, 56.1057 divided by 2. 28.05, we'll say 28.05. So negative 28.05. Square both sides to get rid of the square root. Squared is 786.8. 786.8. And so then I add 9, 786.8 plus 9. I could have done this in my head, but whatever. 795.8. 795.8 is the time at which that occurs. It's kind of a hard problem. Did I make any mistakes? Let's see. Oh, I totally made a mistake. Right here. I mean, do you guys see what I did? I reversed the limits of integration. How you know I've been going too long with the video, right? I'm supposed to be plugging in x and plugging in 10, right? I did it the wrong order. Like I plugged in 10 and then I plugged in x, right? So that screwed me up. So basically, these two terms here are in the wrong order. That's what I did. That was stupid. So it should be this minus 2, and that should give me the correct answer. Yeah, so now so let me just do it quickly. 58.1057. What would you do to solve this equation? You would add 2, right? You would add 2 to it, and then you would divide by 2. And then you would square that result, right? I think is what you would get. You'd square that, and then finally you'd add 9, and that gives me, 912.17. So 912 point whatever. Sorry about that mistake, but I was right to check my answer because I think I've been recording for a long time, and I'm starting to feel my energy level dissipate. I'll do number 2. I think you should just skip number 3. It's a good problem, but it's really quite hard. I think it's maybe a little harder than, I don't know, than the problems you should be practicing. So I would say just focus on other problems. I'll do number 2, and then I can probably bang out the rest of this PDF really quickly. So I might as well finish. So, all right, so this number 2, Mr. Monschauer is making a cylindrical tube in which to store his marbles as he frequently loses them. The volume of a cone is given by blah, surface area given by blah. Okay, suppose Mr. Monschauer has 100 square inches of material to work with. Find the maximum cylindrical... I think we've done this, guys. Haven't we done this a lot of times, right? Look, let me just get you set up, okay? How much information is provided here? Not much. Okay, well, let me at least get you set up, okay? And I think... So, in number 2, you're making a cylinder, okay? Wait. Is it a cone or is it a cylinder? Because it calls it a cone here. But that is the formula for a cylinder. So I think the cone is a typo. I think it's just meant to be a cylinder. Yeah, it's just supposed to be a cylinder. So Mr. M has 100 square inches of material to work with. That's a constraint, guys. That's got to be a constraint. Square inches, is that talking about volume or area? It's definitely talking about area. So that's telling you that your surface area has to be equal to 100. So what you do is you write 2 pi RH plus 4 pi R squared equals 100. That's your constraint. Okay, that is our constraint. The thing that you're trying to maximize is, of course, the volume, right? So your objective function is volume, which is pi r squared h. And this function depends upon 2 variables. So what are you going to do? You're going to solve this equation. For h. It's going to be much easier to solve for h, and then substitute into this equation here. I'm not going to do it because I've already done literally the same exact algebra with the problem in the first PDF, right? So like if the algebra is tripping you up, go look at the cylinder problem from the first PDF because I do all the algebra there. But yeah, this is your constraints. You're going to solve this guy for h. So in other words, move this term over, divide by 2 pi r, substitute into here, simplify as much as you can, then take the derivative only after you simplify, set it equal to 0, and solve for the r value. Now suppose instead the tube must be 100 cubic inches. So what's going, and then find the minimum amount of material surface area needed. What's happening is, in part B, they're switching around the constraint and the objective function. Now the constraint is the volume. Now the volume has to be 100. So in part B, what you're going to do is you're going to say 100 has to be equal to pi r squared h, right? It's the volume that needs to be that. And so then, and it's the surface area that's your objective function. So the 2 pi r h plus the 4 pi, 4 pi r squared. That's not the right formula, right? I mean, now that I'm looking at it, that's the surface area. I mean, if this is a cylinder, that's not the right. It should be 2 pi r squared, right? Not 4 pi r squared. Okay, I'm gonna suggest that you just don't do this problem. Yeah, because so don't do 2 or 3. As far as 5 is concerned, as far as 5 is concerned, you're going to take the derivative, you're going to solve all I'm going to say, I'm not going to do it. I'm just going to give you a couple pieces of advice. Number one, to take the derivative, you need to use the product rule. Let me make sure that you can get the derivative. The derivative is going to be derivative of e to the x is itself times x squared minus x minus 5 plus, leave the e to the x alone, take the derivative of the other guy, that's 2x minus 1, okay? And so you're going to need to, I would maybe, you can factor out an e to the x like right now from those two terms, leaving you with this. And then you can combine some like terms to get this, x squared plus 1x minus 6, I think. And then that factors as x plus 3 times x minus 2. So if you set this equal to 0, this guy gives you a solution for x equals 2. This guy gives you a solution for x equals negative 3. The exponential gives you nothing because exponentials are never 0. So on this interval, notice that the critical point at x equals 2 is not valid. Not valid because it's not even inside that interval. So the values that you're going to test for this first problem are the boundary points, so negative 10 and 0, and this critical point at negative 3. For part B, the interval is different. It's 0 to 5. Part B, now the negative 3 critical point is inadmissible, but the x equals 2 critical point is valid. So you should be considering the critical point x equals 2 and then the two boundary points 0 and 5. You're going to plug all of those into the original function, see which one gives you the biggest and smallest values. Number 6, explain why each of the following functions do or do not meet the hypotheses of the extreme value theorem. So you're just asking, number 1, is it restricted to a closed interval, like an interval including the boundary points? Number 2, is it continuous on that interval? So this guy is restricted to a closed interval. That's good. Is it continuous on that interval? This function is continuous everywhere except plus or minus 4, because plus or minus 4 will make this guy undefined. So yeah, this function is not defined on this entire interval, so it's definitely not continuous on that interval. So this guy does not meet the hypotheses. This guy, same exact thing, except the interval is smaller. This is good because plus or minus 4 don't sit in this interval, so this one, yes. The third one, this interval is not closed, right? Doesn't include the boundary point negative 1, so nope. Cotangent, oh, that's a new one. Okay, the interval is closed. Cotangent is not defined on this whole interval, though. You might remember there are angles that make cotangent undefined, because cotangent is like the x-coordinate divided by the y-coordinate of the point on the unit circle. So if your y-coordinate is 0, it'll be undefined, right? So this guy fails. Cosine x, it's not restricted to a closed interval, so no. Okay, yeah. Okay, that's it, guys. And I'll stop there.